SwayamPrabha. Digital India. Educated India.
Hello, in this lecture, that is lecture 37, we will be continuing the topic that we were discussing in the last lecture, that is lecture 36. So, in the last lecture, we started to try to find out the critical buckling load, that is P critical, for a pin column. Now, we have taken a column of length L, which is pinned at the two end at z equals to 0 and at z equals to L. Two axial compressive load P is applied at the two end. We assume that the column, because of this load, is deforming, and let the deformation be referred as Vz, where V is the deformation which is a function of z, z being the lengthwise axis of the column. Now, we have to see whether it is feasible to have a Vz because of this axial compressive load. Now, we take a small portion of the column and draw the free body diagram. From the free body diagram and the moment balance, we get this equation, governing equation, which in terms of V, or the lateral deformation of the column. Now, let us try to solve this equation. So, this equation can actually be written as now let us replace this P by EI as mu square. So, mu square is nothing but P by EI. Just for the simplicity of the expression, I am replacing P by EI as mu square. Therefore, this equation becomes d2V by dz square plus mu square into V is equal to 0. Now, this is a simple ordinary differential equation, and the solution of this equation is going to be A cos mu z plus B sin mu z, where A and B are the unknown constant which can be evaluated in terms of the boundary conditions. Now, the boundary conditions for a pin column can be written as, let us see what are the boundary conditions for pin column. Now, what are the boundary conditions? So, at z equals to 0, V, the lateral deformation is 0. Similarly, at z equal to L, which is also pinned, V0 is equal to 0. Now, if we implement these two boundary condition, then we have Vz, which is A cos mu z plus B sin mu z, and therefore V0, sorry, this is a mistake. So, this is going to be VL. So, V0 is going to be A, and that is equal to 0. Now, VL therefore is B sin mu L, and that also has to be equal to 0. Now, from this equation, we can say that B cannot be equal to 0, because if B equals to 0, A is already equal to 0, then Vz is always 0. So, it is going to give a trivial solution. Therefore, so this is going to give us a trivial solution. So, therefore, this is not acceptable. So, then what we have? We have sin mu L is equal to 0. To satisfy this, mu L has to be n pi, where n equals to 1, 2 and so on. Now, n equals to 0 is also not a solution. So, let me just write. So, n equals to 0 is also not a solution, because if n equals to 0 is a solution, then again Vz becomes 0 for all conditions. So, therefore, n0 is also going to give us a trivial solution. So, that is also not acceptable. Therefore, n cannot be equal to 0. So, the acceptable solution is that n equals to 1, 2, 3 up to infinite number of integers. So, therefore, we get the solution as Vz is going to be B sin n pi by L into Z. This is the solution we get. We can write this as, so this is the solution that we get for Vz, which is an acceptable solution. Now, let us see what does this solution means. So, let us see that if we have a column, what does this solution mean? So, we have got Vz is equal to B sin n pi Z by L, and we have got that mu is going to be n pi by L. Now, mu in turn, mu square is in turn P by E I. If we remember, we have substituted P by E I as nu square, and that is n square pi square by L square. Therefore, P equals to n square pi square by L square into E I. So, this is the solution for P that we get. So, this is a feasible solution of P that we get. So, therefore, if P is equal to this value, then it is possible to have a lateral deformation, and it is going to be a stable lateral deformation, because it is in the equilibrium condition. Therefore, these are the critical loads, critical buckling load of the pin column. So, therefore, P critical 1 is the first critical buckling load is given as pi square by L square E I. P critical 2 is given as 4 pi square into E I by L square, and similarly P critical 3 is given as 9 pi square E I by L square. So, these are the critical loads of the system. Now, corresponding to P critical 1, my V1Z is going to be some B1 into sine pi Z by L. So, this are nothing but the shape of the buckling load. So, these are the critical loads, whereas these are the buckling modes. So, similarly, V2Z is going to be some arbitrary B2 into sine 2 pi Z by L, and so on. V3Z is going to be B3 sine 3 pi Z by L. Now, let us notice one thing, that this coefficient B1, B2 and B3 has a non-unique value. So, it can take any possible value, and that would be an acceptable equilibrium solution of the system. Therefore, this also corroborates with the physical understanding of the buckling, because in buckling the amount of deformation is not unique, it can be any possible thing. So, therefore, this solution that we get is aligned with the physical understanding of the system. Now, what will happen? So, if I have a pin column and if I apply the first critical buckling load P critical, which is pi square E I by L square, then the deformed shape of this is going to be governed by V1Z, which is B1 sine pi Z by L. So, any of this is an acceptable deformed shape. The absolute magnitude is not unique. So, any of this is an acceptable thing. So, any of this. So, this is the first. So, therefore, this would be the first buckling mode of the pin column. Now, next, if I apply the second critical buckling load, which is equal to 4 pi square E I by L square, then the deformed shape, acceptable deformed shape is going to be like this, either like this or like this, or like this. Again, the absolute value is not defined, the solution is non-unique. So, this is the second buckling mode, which can be written as some non-unique constant into sine 2 pi Z by L. So, this is the second buckling mode. Similarly, the third buckling mode is going to be or like this. and so on. So, the third critical buckling load is P critical 3 which is given as 9 pi square E I by L square, and this is given as V3 Z which is B3 into sine 3 pi Z by L. So, this is the third buckling mode. So, this is the third buckling mode. So, now if we summarize, if we have a column, then we can find out so if we have a pin column, we have found out that one possible equilibrium solution of the column under axial compressive load P is will happen when P is equal to P criticals. So, there would be infinite number of P critical value. The first critical value is given as pi square E I by L square and so on. So, the nth P critical value is going to be n square pi square E I by L square. Now, corresponding to each of the critical load, there is a buckling mode, that is the shape by which according to which the column will deform. Now, the absolute value of this deformation is non-unique. It could be anything, but the shape is fixed. So, now we can also explain this whole thing in a different way. So, let us plot this figure. So, on the x axis, let us plot the deformation. So, let us plot the lateral deformation V z. And on the y axis, let us draw the force, which is the axial compressive force. Okay. Now, if we take the column and start applying the force, so the column is not going to deform till we reach a certain value of P, which is P equals to P critical 1. So, if I keep on increasing the load that is applied in the axial compressive direction, the column is not going to deform. So, we are considering a perfect column. So, column is not going to deform till the P reaches P critical. Now, when the P reaches P critical, then three things can happen. If there is a perturbation given, the column can deform in this direction, the column can deform in this direction, as well as the column may not get deformed at all. Therefore, this point is called the bifurcation point. Because at this point, when the applied load P reaches the P critical point, any of these three things can happen. The column can bend in the left direction, the column can bend in the right direction, and the column can remain undeformed as well. Now, from this point, again if we keep on increasing the load, we will reach another point which will be equal to the second critical load, which is P critical 2. Now, here again three things can happen. The column can deform in the right direction, the column can deform in the left direction, or the column may not deform at all. So, this is the second bifurcation point. And so on. This will keep on happening. Then if it doesn't deform and if we keep on increasing the load, then at P critical 3 we will see another bifurcation point. So this is what happens when a column, a perfect column, is under a axial compressive load. So if the axial compressive load is below the pre-critical value of the column, then the column is not going to deform at all. Now, when the applied load reaches the P critical, then a different situation arises. Then the column can bend in either direction or it cannot bend at all. It can skip that point. And then if we further increase the load, if it does not deform, if it deforms, then it will just fail or not fail. There is this probability, there is this instability, it is most likely going to fail. But if it does not deform, then if we can further increase the load and then go to the second critical value, which is P critical 2, and where again a bifurcation point happens. But this scenario rarely happens, that it is not going to deform, and there is lots of uncertainty at this bifurcation point. We really cannot say beforehand that it is not going to deform at the bifurcation point. Therefore, we will not even target to go beyond P critical 1, and we will design that the load that is acting on the column should not cross P critical 1 to avoid all the uncertainty associated with the fact that whenever the load reaches P critical, it can go to an unstable equilibrium with the slightest perturbation. The slightest perturbation, that a slightest increase from the pre-critical can most likely make the column undergo large deformation and eventually failure. So, that is the reason we need to find out the critical load of a column. As you might have understood, the critical load of a column will depend on the boundary condition. We have found it out for a pin-pin boundary condition. In the later lectures, we will find out for a other boundary condition, that is fixed free or fixed and so on. So, now let us move into a second case where we will be having a column with initial imperfection, and we will see how we can solve the problem due to initial imperfection. So, before that, let me just summarize what will happen due to in a perfect column. So, if we have a perfect column, according to Euler buckling of column or Euler theory, so if we have a column till the point P is less than P critical, there would be no deformation. If only we have a perfect column, we have to keep that in mind. It is a perfect column, and in reality you really undergo perfect, really get to see perfect column. It is near impossible. Now, till P is less than P critical, where P critical is pi square E I by L square for a pin-pin column. Till my P is less than P critical, I have no worry. So, the P, so there is not going to be any deformation. When P is equal to P critical, which is a very theoretical case, then there is a possibility or when P is greater than or equal to P critical, there would be buckling of the column. At P equals to P critical, that is the threshold value. So, it is just the threshold value where the column is still in neutral equilibrium. A slight perturbation after P equals to P critical will cause the buckling of the column. So, this is in summary what is going to happen for a perfect column according to Euler buckling theory, Euler theory of buckling of column, which is the most conventional theory of buckling. Now, as I said, in real life it is rather impossible to find a perfect column or to work with a perfect column. So, now let us move into the next topic, where we will be talking about buckling of column with initial imperfection. So, we have studied perfect column, we have understood what is meant by P critical, how to find out P critical, what is the theoretical aspects of buckling of a perfect column. The next topics will be buckling of column with initial imperfection. So, this initial imperfections could be an initial deformation that exists. So, already the column is slightly deformed, the load might be applied. So, A could be initial imperfection, B could be load is applied eccentrically, or the load is applied with an eccentricity or eccentric load, that is all we can say. So, these are the conditions, these are the corollaries of the theory that we have just studied, which will be studying in the coming lectures on buckling. Apart from this, we will also try to analyze buckling of columns with different boundary conditions. Like fixed free, fixed. So, this will be discussed in the next lecture. Thank you.